Let's start with second order derivatives. This is straightforward if you already know how to differentiate. Let's start with a function like y equals 2x squared. We've learned how to differentiate this using the power rule. So we multiply the coefficient by the exponent and then subtract 1 from the exponent, giving us dy and dx equals 4x. And all that a second order derivative is to repeat this process again. So taking the second derivative. So again, using the power rule here, multiply the coefficient by the power of x and subtract 1 from the power. This gives you the second derivative, and we use notation d squared y over dx squared to represent this. And if we multiply the coefficient by 1, that would be 4. Subtract 1 from the power, x to the power 0 is 1. So the second derivative here would just be 4. Okay, so that's all that second order derivatives are, just repeating the process of differentiation. And you can have third derivatives and fourth derivatives and so on. Just a small note on this notation. You might be confused as to why it's d squared over dx squared. Well, when you take a derivative, you're thinking of it as d on dx, the change with respect to the change in x of whatever the thing is. So usually it's y, but it could be anything there. And if you're repeating that process, then you're taking the change with respect to x again. So you're multiplying d on dx by itself. So you're actually squaring that whole thing. And we're thinking of dx as a singular term. So it's dx squared, even though it looks strange because we don't have brackets there. It is actually, we're thinking of that as dx all squared. Okay, so that's just a little note on notation. A bit more on notation, if we're talking about f of x, then the first derivative is f dash of x, we know already. The second derivative is f dash dash of x. Pretty logical there when you're talking about f of x. Okay, so now let's talk about stationary points. What are stationary points? A stationary point is where a curve has gradient 0. So let me go ahead and write that down. What does this mean when the gradient is 0? So let's have a look at our graph here. This is some random quartic. There's going to be 2 points in this picture where the gradient is 0, at 0, 0, and at this minimum here. Okay, so if we drew a tangent to that curve at those points, it would have a gradient of 0. So let me just get that tangent. There we go. Okay, so there are actually 3 types of stationary points. There are minimums, points of inflection, which is what we call this point here, points of inflection. And can you tell me the third one? If we have minimums, what else goes with the minimum? That's right, maximums. So points of inflection, minimums, and maximums are the 3 types of stationary points. And we actually call these local minimums and local maximums. Well, in fact, for this example, if this was a quartic, this would be a global minimum. But usually we don't have enough information to say this would be the absolute minimum of a curve. So let's have a look at another example. Let me just draw a quick cubic graph. So here we have a local minimum and a local maximum at these 2 points, but they are not the absolute max and the absolute minimum, right? Because the graph continues upwards above that local maximum and below this local minimum. So that's why we call them local minimum and maximum. So those are the 3 types of stationary points you need to be aware of. And what else can we say about these points? Well, when the gradient is 0, we know that the derivative is equal to 0. The derivative of the function at those stationary points. And is there something we can say about the second derivative? So let's think about what the second derivative actually represents. So if the derivative is the rate of change of the function, the curve, what is the second derivative? That's the rate of change of the derivative, or the tangent to the curve, right? So if we look at the tangents to this curve around this local minimum here, if we look at the tangent before that minimum, that will have a negative gradient. Okay, and then if we look at a tangent after that minimum, that would have a positive gradient. So what is happening to the first derivative? What is happening to that the gradient of that tangent? It's going from negative to positive. So when we have a quantity going from negative to positive, it's increasing. Okay, what do we say about the derivative when a curve is increasing? That's positive, right? So when we have the gradient, the gradient of the tangent increasing, that means that the second derivative will be greater than 0. All right, the rate of change of the derivative of the curve. So when the second derivative is greater than 0, this indicates a local minimum. Okay, what about if we had a maximum? So again, let me draw that curve in again. If we had a maximum, the tangent is going from a positive gradient to a negative gradient. So it is decreasing. Therefore, the second derivative is less than 0. This indicates a local maximum. Okay. And what about if the second derivative is equal to 0? Well, this could be a range of things. It could be a minimum, a maximum, or a point of inflection. And let's have a look at an example to show why that's the case. So it could be min, max, or point of inflection. Okay, so let's have a look at an example. Let's look at it at the example x to the power 4. So let's just draw that down here. X to the power 4 looks something like this. So it's like a kind of a U shape. Okay, not too bad. Of course, not very accurate, but this is the rough sketch of y equals x to the 4. We have a minimum here, and let me just get this curve looking a bit straighter here. Okay, something like this. So what's happening at that minimum? Well, if you look at the second derivative at that point, which we can actually do, so let's go ahead and find the first and second derivatives of this function. So f of x equals x to the 4. The first derivative using the power rule is 4x cubed, and the second derivative is 12x squared. So at x equals 0, what values do we get here? Well, they're all 0, right? So f dash of 0 is 0, and the second derivative, f dash dash of 0, is 0. So here we can clearly see from the graph that it's a minimum, but we are getting the case that the second derivative is equal to 0. So around that point, the derivative is not changing, as we would expect from a local minimum, usually. However, we're getting 0, but it is still a minimum. So in this case, when the second derivative is equal to 0, we could either have a minimum, a maximum, or a point of inflection. So you have to be careful with those cases. You have to check the behavior of the tangent around the point. So we're going to have a look at an example of that in a minute. All right, let's move on to our first example. Example 1 says, find the coordinates of the stationary points of f of x and determine the nature of each. Given f of x equals x to the power 3, take x squared, take x plus 1. So we're given a function, and we want to find all of its stationary points and what sort of stationary points there are, either a minimum, maximum, or point of inflection. The first step here is to find the derivative, so f dash of x. We can do this by applying the power rule to each term. If you need a reminder on how to find derivatives, check out the previous videos in this series and the video on the 4 basic rules of differentiation you need to know. So applying the power rule, we're going to get 3x squared take 2x take 1. All right, so next we ask, when is this equal to 0? What are the values of x we get when this equals 0? So when 3x squared take 2x take 1 equals 0, we can actually factorize this nicely. So this factorizes. Factors of 3 and 1 that make 2 are just 3 and 1. So this is going to be 3 times negative 1 plus 1 makes negative 2. So then we get values for x of x equals negative 1 on 3 and x equals 1. The next step is to find the second derivative. and we're going to evaluate what value we get at these points, at these stationary points. So again, differentiating this function here, applying the power rule to each term, we're going to get 6x take 2. And then we find the second derivative at negative a third. So plugging negative a third into this function, 6 times negative a third will give us negative 2. Take 2 is negative 4. And then let's do it at x equals 1. So f dash dash of 1. 6 times 1 take 2 is 4. 6 take 2. And so now we can see the second derivative at x equals negative a third is less than 0. Remember what that means? When the second derivative is less than 0, that implies a local maximum. Okay, so here we can say, let's just make a note. This is less than 0, so this is a maximum, local max. And this is greater than 0, so this implies a local minimum. And now we need to go ahead and find the coordinates of those points. So let's plug in the x values into f of x. So f of negative a third, plugging that into this expression here, that's going to give us negative a third cubed take negative a third squared plus a third plus 1. And if you evaluate that, you should get 1 and 5 on 27. You could just plug it straight into a calculator if you wanted. Then let's evaluate f of 1. 1 take 1 plus 1. That gives us 0, right? So then we have our maximum at negative a third, 1 and 5 on 27. And we have our minimum at 1, 0. So you could even go ahead and make a quick sketch if you wanted to, just to see what that would look like. This is going to be a really tiny sketch, but our minimum is at 1, 0, which is over here somewhere, and our local maximum is at negative a third, about 1, so maybe here. And this is a cubic, so a positive cubic, so it looks something like this. All right. So there we go. We've found all the stationary points and their natures. Okay, let's have a look at another example. This says find all stationary points and the nature on the curve y equals x to the power of 3, take 3x squared plus 3x and sketch the curve. You can give this question a go, seeing as we just went through an example, see if you can manage this by yourself. So first step is to find the derivative. So dy on dx, again applying the power rule to each term. This is 3x squared take 6x plus 3. And then we want to find when this is 0. So when 3x squared equals take 6x plus 3 equals 0. Can we factorize this? Yes, we can. So factors of 3 and 3 and make 6, 3 and 3. So let's multiply the 3 by 1. And they both need to be negative, so that's 3x, take 3x is negative 6x, and we'll get that positive 3 at the end. This gives us values for x of just 1, right? They are both give us, both of the factors give us a value for x of positive 1. So then let's go ahead and find the second derivative, d squared y on dx squared. Applying the power rule to each term, this will give us 6x take 6. And let's see what that second derivative is doing at x equals 1. So when x equals 1, d squared y on dx squared. What is this equal to? This is equal to 0. Okay, this is the special case where we're not sure if it's a minimum, maximum, or point of inflection, just looking at the second derivative. So what we need to do is look at the derivative around the point x equals 1. So what we do is we say when x equals 2, what is the first derivative? So what is the tangent at x equals 2? That gives us 3 times 2 squared take 6 times 2 plus 3. This is 12 take 12 plus 3, which is 3. And this is greater than 0. What about a point just before x equals 1? So when x equals 0, what do we get for the derivative? When x equals 0, we get 3, which is again greater than 0. So that's also positive. So when we have no change in the derivative, that means we have a point of inflection. So we can say, therefore, we have a point of inflection at x equals 1. And let's go ahead and find the y coordinate. So when x equals 1, looking at the original equation, plugging x equal to 1 into that, that would be 1 take 3 plus 3. So that's y equals 1. So we have a point of inflection at 1, 1. So let's have a look at what the graph would look like to get a better idea of what's happening here. So we have that point of inflection at 1, 1. So about here somewhere. And it's a positive cubic. Remember, positive x cubed. So it would look something like this. Oh, that's a terrible sketch. Something like this. Okay. So that's what the point of inflection looks like. It's where the graph kind of flattens out, but it is still increasing for all x. So this tangent here would have a gradient of 0. And if we look at what we did here, so when we looked at the value of the derivative at x equals 2, we were looking over here somewhere. And we got a positive gradient for that. And we looked at when x equals 0, down here somewhere, and we got a positive gradient for that. That told us it can't be a minimum or a maximum because the shape of the curve is not changing around that point. It's still increasing, so it must be a point of inflection. All right, so that's about it for second order derivatives and stationary points today. Hope you found that useful. Please leave a like if you did, subscribe if you want to see more content, and leave any comments with any questions you might have down below, and I'll see you in the next one. Bye for now.